Here we have an image of a very highly slowed down image of pulsars looks like. Initially, they were thought to be aliens who were signaling something to the Earth. Then they came to be known as pulsating stars or pulsars in short. Before beginning the presentation, I would like to say that I ended up 30 slides. So in order to cover that 15 minutes, I will be skipping some slides and concepts which I think are not necessary. If you have any questions regarding them, you still ask me towards the end. If not, then I explain that to you.
And it's actually really have time because some lectures are off, right? So maybe you can continue with that.
So, what in practice, that makes and you can tell me how you want me to
no, you can go on because you need to press time. Again, one of the lectures, lectures of radio. So you can continue to whatever you want. Whatever I want to add to this, I will add.
It was discovered in 1967 by Justin Leonard and Anthony Lewis. They were first sighted in Britain deep men, short for aliens. And then it was as if every radio pulsar was looking up, every radio telescope was looking at pulsars, so they came to be known as pulsating stars. This led to the 1974 Nobel Prize controversy, which is an interesting discussion in its own. In 1974, the Nobel Prize for the discovery of pulsars was awarded to Anthony Lewis alone and not to Justin Leonard. And it became a worldwide controversy because the obvious reason that was thought was that she was on the receiving end of blatant gender discrimination. She would have received the Nobel Prize had she been a man, which is why I in fact chose this topic pulsars. Just last year we had a meeting at Viva for International Astronomy Union that was decided by Dr. Helen Mason, whom Ma'am already talked about, and she specifically lent weight to the severe lack of women in astrophysical research. That's why I chose this topic as I'm going to Justin Leonard and Stephens. Pulsars are rotating and highly magnetized neutron stars emitting a beam of electromagnetic radiation. Neutron stars will require the right combination of rotational frequency and magnetic fields that are high enough in order to emit a beam of radiative jets, which are a distinguishing feature of pulsars that distinguish them from neutron stars. The characteristics of pulsars are similar to the characteristics of neutron stars. The main characteristics we need to look at are the magnetic field, which is about 10 raised to 11 to 10 raised to 14 Gauss. This can be compared to 0.6 Gauss for the Earth. And the rotational periods vary from 1.4 milliseconds to 8.5 seconds. The fact that the pulsars observed in the millisecond period tells us that these, despite their large mass and various intensity, are rotating about 1,000 times every second. This is a comparative picture that shows the comparative sizes of white dwarf Earth and a neutron star. The typical size of pulsar. Light of model is a very fundamental concept for the understanding of pulsars. Turned out that the pulsations were not because of the change in periodic intensity with respect to time emitted by the pulsar. The emission of radiation does take place continuously, but it is detected periodically by the observer on Earth, and hence they are perceived by us as pulses. The names of pulsars generally begin with the letters PSR, short for pulsating source of radio. They are then followed by a single letter that denotes the time epoch or the year in which this pulsar was recorded. J denotes the 2000 epoch and B will denote 1950 time epoch. The following four digits denote the right extension coordinate of the pulsar. So 1921 will give 19 hours and 21 minutes. The following sign of four digits give the declination coordinate of the pulsar. Plus 2153 will tell you that the pulsar is 21 degrees 50 minutes north of the celestial equator. Minus will tell you it lies below the celestial An interesting thing to note here is that the time clock is generally 2000 or J, with the definition is given in 4 coordinates. And if it is 1950, that is B, and definition is generally given in 2 digits. That is because the instruments then were of having less precision, so they would only record the definition in minutes. But today we can make those measurements in, they could record them in degrees, today we can note them in degrees as well as minutes. Here are some keywords which I was planning to say, but I guess some out of this anyway. Nuclear pasta. The density of pulsars, which are basically neutron stars, in the previous slide was shown to be 10 raised to 14 grams per centimeter cube. This is the same as the density of nucleus, which is why pulsars are giant nuclei of the size of city, which is a very strange concept in itself. Which is why you expect a matter inside the pulsar to also be strange. The strange matter inside the neutron stars usually is believed to be in the structure of flat sheets, spirals, and small nuggets. Because of their similarity to corresponding structures of pasta, this strange state of matter is known as nuclear pasta. So we have solid liquids and gases on board, and high temperature plasma, low temperature boside matter, and this is thought to be a state of matter that exists exclusively inside the neutron stars. This was sound of pulsar. The speed is not working, so I get to this at the end. Anyone wishes to know. Pulsar radius. Initially, for about 100,000 years, the pulsars radiates very intensely and it's spinning very fast. For the next 10,000 years, 10 million years, it eventually begins to slow down and it starts emitting in radio, and we'll see how that goes. Since most of the pulsars we see are emitting intense radio, we believe this to be the middle age life of a pulsar. At the end, they die, which means that they slow down so much that they enter what is known as a pulsar graveyard stage. Unless, of course, a neighbor breathes new life into it. This is what are known as black widow or redback pulsars. Black widow or redback are keywords that are derived from the corresponding species of spiders. These spiders are special because in this particular species, the female is known to devour her male companion. And this cannibalistic instinct is also observed in pulsars, meaning that if there is an object like a star or nearby, like a red giant, then it siphons energy and matter from its neighbors and gets in life. Siphon meaning attract or pull in a pipe-like manner, which is shown in the image that I have. And new life, because if it has entered the pulsar graveyard stage when it's very slowed down, then by resurrecting or recycling, what it does, it makes even higher angular momentum because it's getting more mass, and then it starts spinning again and it will start emitting radio again. So it's like it's breathing new life into it. Finally, low mass X-ray binaries are the pair of objects that are involved in such resurrections. Millisecond pulsars. So even we proved was special for the time period, but millisecond pulsars are another type which are believed to have been resurrected or recycled because they are seen to be having an isolated existence with absolutely no visible companion nearby. So they may have all the mass that is around them and have gained extremely high velocities, which is why they become millisecond pulsars. Then there are X-ray pulsars, which are giving a periodic fluctuation X-ray pulses again. This again is because of resurrection or recycling, as you may have seen in the previous GIF. The initial beam radiation is radio, and then it starts siphoning matter, then you get a narrow X-ray jet. So these type of pulsars are also observed in which you have radio emission, and then suddenly the radio mode sort of switches off, and the X-ray mode switches on, like a switch. So those type of pulsars are called X-ray pulsars, and they are not very common. Then rotating radio transients. These are pulsars that do not glow periodically. This was something. So last year I was selected for summer school at Viva, and there were different lectures. One of them was by Dr. Fergusson College, who specifically talked about transients. One of the type of transient was rotating radio transients, pulsars that do not glow periodically. This is the main slides that I'll be focusing on, this one and the next one. Why are the white dwarf? How can we say with full confidence that pulsars are neutron stars? Because even white dwarfs are highly compact objects. The video will show you the cliche example for conservation of angular momentum, and the ballerina will put her arms in, she spin faster. And that's a key concept for us to know, because when she does pull in her arms, she requires to exert more strength and energy to keep her arms in because of the centrifugal force, and that is a very key concept for disproving white dwarfs as pulsars. This is a proof. So let's begin with the basics. A pulsar will exert existing equilibrium compared with the outward centrifugal acceleration and an inward gravitational acceleration. Now, in order for it to move very fast and to stay in equilibrium, you want the centrifugal force to be very low and the gravitational force to be high enough that it can balance it. Centrifugal acceleration is omega square r. We want omega to be very high for pulsars, so r should be low. Gravitational acceleration is g m upon r square. We want this to be high, so mass has to be high, radius has to be low. When you derive a formula for omega, you get it into a function of m upon r3, which is reminiscent of density. Typical densities for white dwarfs are of the order of 10 to 7 grams per centimeter cube. When we get omega equals 0.82 per second, giving the corresponding rotational period of 7.7 seconds. This is very key because we know that if we have the white dwarf, then that is the type of period we will get. Now let's run this derivation backwards. Suppose we have a millisecond white dwarf pulsar. Then we want the time period to be in milliseconds. So omega should be increased by an order of 1000. So our density has to be increased by a higher factor. And that sort of density is not observed for white dwarfs. As we've seen before, for neutron stars, they have densities like 10 raised to 14. That is the sort of thing that can give you millisecond pulsars. So, for a white dwarf, balancing the centrifugal and gravitational forces tells us that the centrifugal force during second period would be so large and overwhelming that a white dwarf would not remain intact under its own gravity. It's just way too huge. It will have a huge centrifugal force and correspondingly less gravity. So now that we have proved that these are necessarily neutron stars, how do we distinguish between them? All pulsars are neutron stars, and not all neutron stars are pulsars. As we have seen before, neutron stars will require the right combination of magnetic field and angular momentum, and the direction of the energy beams also matter. They need to sweep across the earth for you to see it, because you don't want to see only the radiating jets. Neutron stars are very small objects at high distances from us that we ordinarily cannot see. We can see pulsars, and that's how we see neutron stars. A neutron star will be there like an incandescent bulb, whereas a pulsar is like a laser, which is necessarily has to be directed at us. Here is the estimation of the magnetic field. So this is another derivation that one can do. I won't go over another derivation because I don't want to cut around this. But the main thing is at the end, the magnetic field turns out to be of the order of 10 raised to 18 tau if we consider pulsars to be neutron stars. That tells us that further confirms that pulsar stars have to be neutron stars because pulsars are observed to have magnetic fields of the order of 10 raised to 11 to 10 raised to 14, as again we've seen earlier. White dwarfs would simply be too large for them to have such high magnetic fields. Synchrotron radiation is what's special about the pulsars. So why are the jets so special? A very high magnetic field that's rotating at very high frequencies is observed only in pulsars. These will induce insanely strong electric fields. These electric fields in the open magnetic fields coming out of the magnetic poles will accelerate charged particles to relativistic speeds. These are then ejected outwards. While doing so, they gyrate around the magnetic fields with very high velocity, giving emission which is highly polarized and is known as synchrotron radiation. It is termed as synchrotron radiation because of the gyration motion of charged particles, which is the principal population of synchrotrons. Another natural question to ask, since it's an isolated system, you will have conservation of energy. Energy is being given out in the radiative jets, then what is the source of this energy? First of all, it could be the loss of gravitational energy. This would cause the pulsar to collapse. The collapse would lower its moment of inertia because the conservation of angular momentum, its angular speed will increase and it will decrease its spin period. On the other hand, it could lose its rotational energy, which would obviously cause it to slow down. So we look for such evidences out of the stars. On the right, we have three images, the top one being a broad view of the crab nebula. When we zoom into the center, we have the second image from Hubble optical. The right one from the two center brightmost stars is the crab pulsar. When we zoom in on that, we have the third image, which is a composite of optical Hubble, infrared spitzer, and X-ray from Chandra. Here you can see the spinetras, the high energy jets, as well as the central neutron stars. When we make observations of this, we realize that the crab nebula is slowing down at 38 nanoseconds per day, which confirms the fact that it is the loss in rotational energy that's powering the radiative jets. This loss of rotational energy is obviously very low, so the energy from the radiative jets is bound to be in the radio region. Why radio? The pulsars are very hot objects and they have a temperature maximum in the UV on the or the X-ray. But the thing about its emissions in other spectral regions is that these span across a larger area and are hence dimmer and difficult to observe, like we see to the right, in the three images to the right. Again, these are the images of the crab pulsar. The one in optical, second one in X-ray, and the third one in the radio. Even in radio, we see that if the jets are not pointing towards us, then the radio simply forms a diffuse cloud above the pulsar. So you won't see the entire pulsar in radio either. It's the beams that we see which are the radio. They are powerful, bright and narrow, plus highly polarized with synchrotron radiation and act like radio beams. This in itself is interesting because the lasers we learn at higher wavelength prefers the lasing action, but pulsars behave like a physical manifestation of galactic radio lasers. Even with radio, the beams do not see across the Earth, then astronomers will see them. These are some applications of pulsars. I already read you about the motivation of why I chose pulsars, but I realized as I went on reading that it has so many applications and it is a hot topic of research, which turned out to be a pleasant surprise. Detection of neutron stars. You can't see neutron stars otherwise. They were just a hypothesis before something that was thought of. With pulsars, they became observed. Secondly, they prove the existence of gravitational waves. This is again another development. Then you have galactic mass, and for that, I have an image on the right. That is an image of that is shown on the Pioneer case of the Voyager Golden Record, which had just been sent into space. At the center of that image, where all lines intersect, is the sun. And at the end of each ray is a pulsar that is denoted, I think, by dots with its unique spin frequency. This is a way of probably communicating our location to another intelligent species or aliens if they were anywhere in a coordinate-less system. Coordinates are man-made, how do they know where we are? So pulsars will form sort of like galactic four-dimensional space-time maps. It will also give our existence in time because the spin period is daily, like I have already talked about. They also form galactic clocks. In fact, millisecond pulsars are known to have precisions higher than atomic clocks. Next, they are used for very accurate distance measurements. They can be used as interstellar helium probes and for modeling the distribution of galactic electron density. If you have questions regarding that, you could again ask me that I'll explain that. Probes of space-time and gravitational wave detectors. This is something very unique and it's very happening right now, which is why I discussed that. Pulsars are the unique marriage of intense gravitational fields and equally intense electromagnetic fields. So if there's something like gravitational wave being created nearby, or if it's close to a black hole where it's experiencing space-time curvature, then it will interact with that because of its extremely high mass. At the same time, we will see some changes in its electromagnetic spectrum. Thanks to its high intensity, we can record that at sufficiently high precision, and we can use pulsars to observe space-time curvature or we act as gravitational wave detectors in the sky. I have listed down some current research trends in here. On the right, the first image is of Astrosat that was launched in 2015. Second image is of the X-ray telescope. Last year, the first white dwarf pulsar was observed, as we expected, had a high time period, 1.95 minutes, and it does not emit an X-ray or gamma ray. Then, I talked about X-ray pulsars. So, in order to study X-ray pulsars, we need precision instruments, X-ray detectors, which we did not have in the earlier peak of 1950. So, there was a lot of focus on X-ray telescopes and gamma ray telescopes. It is currently there right now. These are some X-ray telescopes that have been launched. There has already been a seminar on study of pulsars and then period with the use of Astrosat data. Next, searches for pulsars within 0.01 parsec from Sagittarius A star. Again, there has been a seminar and Pam has already talked about Sagittarius A star is the location of the supermassive macula sector of our galaxy. So when we look for pulsars within 0.01 parsec of that, know that there is some very close to the central black hole because the overall diameter of our Milky Way is 30 kiloparsec. Very close in order to be able to study the black hole. So when you look at the pulsar, they will act like space-time probes or space-time curvature at the center, and we study the black hole. Then examination of emission mechanisms. This is also a very hot topic because the emission in this spans wide, has a wide range, and all of the emission in different spectral regions is because of different mechanisms. Even the dip radio, the one in jets is of different mechanism from the radio curve. And none of that has been explained with full confidence. Electromagnetic counterparts of gravitational wave sources. Again, this was a lecture in South School that I had. This one was given by Raka, who was working with Dr. Fergusson specifically on this particular topic. That's how I know of this. Electromagnetic counterparts, like I've already said, you study gravitational waves and use pulsars as detectors in the sky to detect the gravitational wave there and transmit the information to you, which you record in your electromagnetic spectrum. Finally, Pulsar Observatory for Students is an annual program organized by NCRA, where they invite some select winter school students to carry out live pulsar observations with a sensitive radio telescope and radio astronomy center to radio telescope. This is again in order to encourage more people to take up radio astronomy and pulsar being a large part of radio astronomy. This is also a current project that's going on. This is the International Pulsar Timing Array. The telescopes in here are all participants that form the array together. This array is particularly dedicated to the detection of gravitational waves in the radio region of the electromagnetic spectrum. We can also see that the giant Neutron radio telescope in Pune is also participating in this. These are the takeaway points. Galactic lighthouses, nomenclature, pulsars, are neutron stars with synchrotron radiation. Spin down is is another keyword actually, whereas pulsar basically just slows down. So that's the name of pulsar known as penta. They act as radio lasers, which is rare, and they have a wide range of applications and research. These would be the references. My lectures in Sanskrit were Anjali notes. The book by Vaidyanatha Asu. I also refer to the SCRI website, and the next website is that of the Jordan Land Center for Astrophysics. That has 4 websites on pulsars and then 2 more. Thank you. And questions are better.
This is one point again. Pulsars and neutron stars, the neutrons and vice versa. So can you just throw more light on that? Very clearly, not for this straight for to understanding the students. So this has to be this necessarily is the
So neutron stars that are spinning fast enough and have very magnetic fields will emit jets. Those are pulsars. If those jets can be seen by you or are directed towards you. That's so not all neutron stars will be pulsars, but all pulsars will be neutron stars.
Every treatment should be automated. Sales.
Yes.
You check the difference.
No, I think it happens in all X-rays. It's not one specific wavelength. I'm asking. It's not one specific wavelength.
So you have all the different.
Each time there is an emitting gamma. Gamma to radio.
So most of the time we don't have so many observatories of gamma that is observing the pulsars. Most of the observatories observing the pulsars are optical ones and the radio ones. So most of the work in pulsars is done by radio astronomers, not other currents.
They are also trying to add astrosat data for the X-ray part.
At least also something about the central propagation.
I have a picture of a magnetic field of a neutron star or pulsar. It's very high. The key thing in here is that the magnetic poles do not coincide with the rotation. So as it rotates, in some of them it's physically the magnetic poles rotate around the rotational axis. Now you have a change in magnetic field changing in both magnetic field and direction. Now Maxwell's work, such a field will induce electric field. Now this change is very high. You have high magnetic field and high speeds. So you have very high electric fields. In the poles, loops that we have, now electric fields will accelerate charged particles everywhere. In these charged particles will go around the magnetic field lines. So in the poles lines, this is not an issue. So charged particles will be carried from south to north or north to south based on the sign of Earth. But in the open field lines at the top and at the bottom, very close to magnetic field lines, they will move up magnetic field lines, so they will never come back. So they are thrown out and back to relativistic speeds. When they are doing so, they follow helical path. Yes. So that sort of motion gives you highly polarized radiation. That radiation is termed as synchrotron radiation by us because similar that is found for the principle working of synchrotron radiation. Synchrotrons, the most popular one being the Large Hadron Collider. So we use that very principle. As in sound of pulsars, so really find So first of all, sound of pulsars is another very interesting pattern of pulsars that I came across on the Georgia Lang Center of Astrophysics website. And I wanted to specifically listen to this. Can you here is this is what the Veda pulsar sounds like. Different pulsars sound different, and I'll tell you why that is. And what exactly is that sound that we're talking about? Because they're not scientifically conjugated in a way. First, because there's no medium in between. They require medium in between. So what is done is that they make an instrument similar to a radio. The radio will take radio frequency from an FM channel and convert it to audio. Similarly, you can use that and build a scientific instrument that will work on the same principles. It will take the radiation from the radio jets that are coming in and it will convert that to audio waves in such a way that the intensity of radio waves is going to be proportional to the amplitude of the sound waves that you are hearing. This was the sound of the Veda pulsar. Now, since we are converting the same radio jets into audio that we are seeing ourselves with the radio telescopes, these are meant to coincide. This is a now show video that's a plot of how the intensity of radio is varying, and at the same time, we also hear the audio. This is from Veda pulsar. It's a millisecond pulsar. It's an extremely slowed down version. These are observations from the Parkes telescope in Australia, which was one of the participants in the 90 carrying time. So this analysis has been done by Jordan Laxon. And this goes on like this. You can also see the periodicity with which this is varying. You don't have missing peaks in here. So this is one. There are, I think, about 7 different types of sounds of pulsars, broad categories. Obviously, you have the frequency. So I'll play one more for you. This one is slower. So it has a higher rotational period, and we'll see how that one sounds. This one has been taken with the double so my daughter back themselves. So here you have a lower frequency. Again, there is a variation in the peaks. So, like we said, it's the millisecond pulsars that I use just blocks because they have very high precision. And with this, if you just focus on the audio, it sounds as if the pulsar is sounding like a heartbeat. For a craft computer which is rotating extremely fast, when you slow it down to this extent, it still sounds like white noise because you are not able to resolve those pulses. So it sounds like white noise, so you need to slow it, and even more you need to go into slow mo in order to actually be in a position to resolve those pulses. So this was the sound of pulses.
Yeah.